Alright, next, there's something called SSL or TLS. So what exactly are SSL and TLS? Here, SSL, also known as TLS, are actually encryption protocols. SSL is called Security Socket Layer, which is the security layer. The security layer, meaning TLS, is called Transport Layer Security. These two things actually, you could say TLS is a public version of SSL. The SSL protocol originally was developed by a browser developing company called Netscape. Back then, our web page traffic, generally used the HTTP protocol, which is plain text, meaning its data is actually not secure. Later, when Netscape developed SSL, it was to ensure the web's security. Previously, many web pages were HTTP, right? And now when you open a web page, generally speaking, they are HTTPS, like when you open a web page through a browser. Here, it says the connection is secure, right? Why? Because the S in HTTPS is actually SSL. HTTP over SSL, in short, is HTTPS. Previously, many of our web pages in earlier years, say about a decade ago, many web pages were HTTP. You might open one and find that the page could have many enticing small ads. Honestly, this HTTP was not secure. First off, its data was not encrypted. Secondly, the web pages could not verify their identity authenticity. Why? Because here's the thing. If you use HTTPS, first off, the communication between you and the server is encrypted. Secondly, HTTPS must have a certificate. So SSL, why does it need a certificate? Because SSL must have a certificate. That is to say, if a website uses HTTPS, it must go to a certificate authority, find a CA to apply for a certificate, then it will link its certificate with its domain name. At that time, when you open a web page, the server needs to provide its certificate. If the website's certificate is legitimate, it means the website is not an imposter, not a phishing site. But if the website's certificate you cannot verify through the respective certificate chain, then the website might have issues. So through SSL, this can protect the security of HTTP. Later, SSL has evolved to protect other types of data communications, like there is a VPN called SSL VPN. This VPN uses the SSL protocol, and we previously discussed this. HTTPS, its traffic is encrypted. Fundamentally, it's because of SSL. SSL can encrypt this data. Thus, we can use SSL to encrypt our communication traffic, which led to the development of SSL VPN technology. Okay, so here, this is SSL. It is called the Security Socket Layer. Why is it called that? Because originally our HTTP packets were encapsulated how? On the outside, it's MAC, right? But this is the data link layer header. Then it's the network layer header. Inside, it's TCP. Why? Because HTTP is based on TCP, what TCP port 80, right? TCP, destination port TCP 80 explains. It explains that this packet is HTTP. That means, in our network, each layer, every layer's header will have a piece of information to identify what the next layer's header is. Like in the network data link layer header, it has something called ether type. Layer 2, this is called Ethernet. To be precise, let's be precise. Layer 2 might not always be Ethernet, right? In Ethernet, it has something called ether type. Ether type is used to identify which protocol is on the layer above. So if it's Ethernet, it's Ethernet. The header, then IP header. In the IP header, it has something, what is it called? Protocol number, right? Then the transport layer header. In the transport layer header, it has port numbers. The transport layer header uses port numbers to identify. Then inside HTTP, in the header, it has its own things like what method and stuff like that. So this thing actually, it's already at the application layer. This thing we should not analyze it solely from a network perspective, right? This thing belongs to the application layer. Because in our TCP IP model, from the transport layer upwards, it is the application layer. At this point, our HTTP protocol, based on TCP, uses port 80. But if we talk about SSL, how does SSL encrypt HTTP? SSL operates above the transport layer. It inserts an SSL header here. Okay, then this SSL header, of course, is different from HTTP, right? Here, the port number changes to 4443. SSL's port number is 443. Generally, encrypting data follows a pattern, somewhere in the network, inserting a header to tell you how this data packet is encrypted. Then the part before this header is plain text. The part after the header is encrypted. So by inserting such a header, outside of this header is plain text. Inside of this header is encrypted. No matter which layer of the network you encrypt, if you say you encrypt at the data link layer, right, at this place, you say at this place, insert a header here, the back is encrypted, right? You say network layer encryption. After the network IP header, we insert a header, then the subsequent data is encrypted. You say transport layer encryption, right? Hey, I insert a header here. Hey, isn't this just like SSL? So here, SSL, it operates at our transport layer above the net, inserting such a header inside it. So this thing called the security layer, security socket layer, not a layer, security socket layer, not layer, security socket layer. Below this, TLS, what is it called? Transport layer, security. So what is TLS and what is its relationship with SSL? Regarding SSL, it was originally a private protocol. SSL is a private protocol. Later, it was made public. And after being made public, it became TLS, simply put. That is to say, SSL evolved through versions 1.0, 2.0, and 3.0. Later, this TLS is essentially a variant of SSL 3.0. So TLS could also be called SSL 3.1. That is, TLS is based on SSL 3.0, modified from that foundation, modified from that is modified from that. As for TLS, it is a public protocol. It can be considered SSL 3.1. Before that, SSL went through versions 1.0, 2.0, and 3.0. That is, SSL or TLS is meant to ensure data security through a protocol. Initially, it was used with HTTP. Just add an S to HTTP. And not just HTTP, many protocols like FTP, right? It can have an S. That is, it can also have an S. Many protocols just add an S, Often what does it mean? Some protocols just add this S. This S is SSL. So this SSL or TLS, they both are. They are similar technologies. Both ensure our data security at the transport layer. Now, regarding SSL, what is its working principle? As a user, you need to first establish a TCP connection with the server. This requires a three-way handshake, right? Establish an end-to-end connection. At this time, the server must provide its certificate. Why? Because it needs to prove its identity is legitimate. At this point, it's about the server proving the legitimacy of its identity. Then the user, through verification, at this time goes to verify the server's certificate. Then he can obtain the server's public key from inside the server's certificate. At this time, it's like saying the certificate itself about the certificate. It can verify the server's identity as legitimate. Why? Because the server's certificate contains its identity information and public key binding. It is signed by a CA. At this point, after the user obtains the server's public key, he will extract the server's public key and then generate his own key. He encrypts it with this public key and sends it to the server. Essentially, what does this mean? It means here is the user and here is the server. One side is the server, one side is the client. When they start, they go through a three-way handshake, right? They establish an end-to-end connection through a three-way handshake. We won't go into that here. And after the connection is established, the server first sends its certificate to the client, pushing the certificate to the client. He pushes the certificate to the client. It is the client's responsibility to verify the legitimacy of the certificate. If the certificate is valid, then he has the public key, right? After obtaining the public key, he uses it to encrypt his own key through this encryption process, and then sends the encrypted key through the public key found in the certificate to the server. The server then uses its private key to decrypt it. This means that the server safely obtains the shared key. So on the server's end, the server then has securely received the shared key. After obtaining the shared key, they can then use symmetric encryption algorithms to secure their communication. Of course, the negotiation is somewhat more complex. We're just simplifying here. If we were to negotiate SSL at this point, why does it require a certificate? On one hand, it's to prove the server's legitimate identity, and on the other hand, it allows the server to carry a public key, which it uses to encrypt the user's data. On this side, the user accesses what? The TCP43 port. TCP43 port is used for SSL. The server provides a certificate, after which the user verifies the certificate. If there's no problem, then he submits a key, which he creates himself. He submits this key to the server, and from then on, they use this key to use symmetric encryption methods for their communications. Of course, the actual negotiations might be more complex, including various protocols and negotiating things like algorithms. These negotiations can become quite intricate. They can base their communication on these keys using symmetric encryption. As mentioned, the negotiation process can be complex, involving various elements, including specific algorithms. These are what they negotiate. So, let's simplify it here first. That is to say, our certificates can be used in SSL. That means on our current web pages, these HTTPS and such are all they are all encrypted through SSL. Well, however, if we're being precise, generally it's mostly through TLS. Why? Because it is a public standard. It is so often what's called SSL, real SSL, is actually quite rare. Most of the time, if you're precise, it's TLS. But we can't just change the name just for that, can we? You say, I want to deploy a TLS VPN, and people ask, what is that? You say, I want to set up HTTP over TLS. Then what's that? You shorten it again, and no one recognizes it. Honestly, there's already a problem with vocabulary inflation, right? With technological advancement, vocabulary expands. It's vocabulary inflation, right? With our technology evolving, vocabulary expands. This thing is already intense, and now you've come up with new terms. Annoying, right? But honestly, vocabulary inflation isn't something we need to worry too much about in Chinese. Honestly, Chinese doesn't need to worry too much. Like in English, alphabetic languages, vocabulary inflation is actually very severe. It's so severe that it's almost like every field is a world apart. Even though this thing, it doesn't really bring any new tricks. So what's called SSL nowadays is likely TLS, but if you really say there's a difference between them, there is still a difference. Not much. Well, besides, there's a concept of key length. Key length is usually expressed in n power of bits and bits. N is how many powers of 2, because our computers are binary. We don't argue, right? We're not going to argue about ternary systems or anything. Here, our computers are built on binary systems. Built on a binary system, so in binary terms, it's a matter of how many bits or powers of 2. Every additional bit you add doubles the size of your key space. For instance, consider the difference between 128 bits and 129 bits. The space difference is significant. No one would think that IPv4, which is 32 bits, compared to IPv6, which is 128 bits, is only 4 times larger than IPv4. What a joke that would be. One was barely sufficient by the late 90s, and the other is considered to potentially allocate an IP address to every grain of sand. Every bit increase doubles the key space. Now, with the encryption algorithm choice being public, the longer your key, the harder it is to brute force decrypt. The computational power required would also be significantly higher, talking decades to crack, which is practically useless. However, if your key is very long, then your encryption and decryption speed slows down. So, based on security needs, we need to choose the key length wisely. For example, someone spending 60 to 70 years to crack it versus thousands of years doesn't really make sense. Even if it's your browser history, what's the point of those records being made public after 70 years and disclosed after 1,000 years? It wouldn't really affect you either. Here, I'm just giving an example. We need to choose the key length wisely, considering your encryption and decryption speed. The shorter your key, the easier it is to break, but the faster the computation. Longer keys are harder to break, but they slow down the computation. Based on security needs, we should choose the key length wisely. It's not advisable to set it manually, because manual settings are vulnerable to dictionary attacks which target common human patterns. The more random and gibberish-like, the better the password. One approach is to let computers automatically calculate keys. This applies to network devices as well. Let routers and firewalls negotiate keys on their own. The keys they negotiate tend to be randomized, making them much harder to crack. Therefore, it's difficult to break such encryption. So today, we've mainly discussed the basic principles of cryptography. Of course, in our upcoming CCNP to CCIE stage courses, there's a chapter on VPN where we will delve into more detailed explanations and practical operations with lots of hands-on practice on how to configure encryption and such.